My name is Jeff Donato. I am the Director of Safety Products at H2 Scan. I spent most of my time in the battery industry with stationary and energy storage batteries. I've also spent a number of years on the IEEE standards committees when it comes to safety of battery products, which also includes hazardous mitigation of hydrogen. So today I want to talk about the different types of hydrogen detection systems that are available and their applications when it comes to safety. As we know, there are many applications that hydrogen can be used, whether it's for using hydrogen to create a product, using it as a fuel, or using it to produce energy for other green initiatives. There are many applications that require different kinds of sensors, response times, sensitivities, and also making sure we don't have cross sensitivities. So we're going to go on and talk about the different technologies of sensors, some of the challenges, as well as some of the regulations surrounding some of these applications. So we need to discuss some challenges. The first one I wanted to address is high temperature environments. Hydrogen molecules can disassociate at high temperatures and can lead to inaccurate readings. Also, with high concentrations, the sensor could become saturated, again leading to an inaccurate reading. Also with cross sensitivities with other gases, some sensors are more sensitive to other gases being present. When it comes to certifications, not all sensors have the same certifications or meet the same standards. These standards can be very application specific, or they could be specific to your AHJ meeting a certain safety standard for their area. Selecting a hydrogen sensor has a lot to do with which application you're going to put it into and the type of properties and responses that you require from the sensor. So the first one I want to address is the TCD hydrogen sensor. So TCD stands for thermal conductivity detector. However, TCDs are not very sensitive typically. They can detect concentrations from 100% down to about 100 ppm. They work by comparing the thermal conductivities of two gas flows, the pure carrier, which is the reference, and then the sample. So different gases have different thermal conductivities, and the thermal conductivity of a gas mixture is a weighted average of the thermal conductivities of the individual gases in the mixture. Catalytic bead hydrogen sensors measure the concentration of hydrogen in a gas mixture by detecting the heat generated when hydrogen reacts with a catalyst. So the catalyst is typically a metal oxide, such as platinum or palladium. These sensors have been used for combustible gas detection for about 50 years. They're very accurate and reliable. They have typically a 3-year life expectancy, and over time the gas sensors degrade and become less sensitive to the target gas. They require more frequent calibrations. Typically a catalytic bead sensor will have to be calibrated every 3 to 6 months. Solid state precious metal sensors are a type of sensor that use the catalytic properties of precious metal to detect hydrogen gas. The sensors work by passing the gas mixture over a thin film of precious metal. When the hydrogen molecules come into contact with the metal, they dissociate into hydrogen atoms, and then these atoms react with precious metal to form the metal hydride. And the formation of the metal hydride releases heat, which is detected by a temperature sensor, and the amount of heat released is proportional to the concentration of hydrogen in the gas mixture. They are very sensitive to hydrogen and can detect concentrations as low as 1 ppm, and they're also relatively fast at responding and can detect hydrogen within a few seconds. The solid state precious metal sensors are durable and have very low maintenance and long lifespan. So the maintenance required by hydrogen sensors is a key factor in your total cost of ownership. When looking at catalytic bead hydrogen sensors, they have a very high maintenance requirement. The frequency of calibration will depend on the operating environment and the required accuracy of the sensor. These sensors should also be cleaned and replaced according to the manufacturer specifications. In my experience, oftentimes we see replacement happening every 3 to 5 years. TCD hydrogen sensors require regular calibration to ensure their accuracy. Again, the frequency of the calibration will depend on the operating environment and the required accuracy. And also the TCD filament should be cleaned and replaced according to manufacturer's guidelines to prevent contamination. Solid state precious metal sensors have a variety of requirements depending on which one you choose. The frequency of calibration is also dependent on the same factors. However, there are some solid state sensors that do not require field calibration. They simply are replaced after the expected life. Some will require calibration, and then there are other solid state sensors that calibrate themselves or perform what we call an auto calibration. So when we take a look at regulation, obviously we have federal regulations we have to abide by when it comes to OSHA and the EPA. OSHA, of course, is about personal protection, whereas the EPA is about protecting the environment. When you get into the state and local fire codes, local municipalities and cities have the ability to add to these model codes and adopt them into law. The reason they are able to add to the code, they may have certain characteristics to their city or municipality that may warrant additional regulation. This is typically afforded to them through home rule, which is either in the state constitution or legislation. Home rule basically states that as long as they meet the minimum state code, they can enact additional laws or regulations to their local areas. You'll see this a lot in cities like New York. Also, Los Angeles and Denver, Colorado often have additional regulations to their area. We'll notice that there are two main fire code model codes that are adopted by governments, either the state government or local municipality. The International Fire Code, which is written by the International Code Council, and then also the National Fire Protection Association. An interesting fact about the National Fire Protection Association is that it was established in 1896 with a primary purpose of creating standards for sprinkler systems and then electric safety and related hazards. I made note that in the IFC, Section 2705 has to do with regulations for hydrogen fuel cell vehicles, fueling stations, and also hydrogen storage. And also IFC Chapter 608, which is, I believe, 2018 and prior. And then Chapter 12 is the most recent chapter in that section to deal with battery room applications. And that is to mitigate hydrogen to keep it below 1% of room volume or 25% of the LEL. There's also the corresponding IEEE 1635 ASHRAE 21 joint document between IEEE and ASHRAE that identifies the ventilation standards and requirements for battery rooms to meet the hazardous mitigation plan that's required for the fire code. And then, of course, the competing National Fire Protection Association model code also has the NFPA 2 for hydrogen technologies, and then NFPA 855 for stationary battery and energy storage systems. In addition to the International Fire Code, there are other international regulations related to hydrogen safety. There are 3 EN standards that provide guidance on anything related to storage and operation of distribution and refueling of hydrogen. In Japan, the Fire Service Act, the Industrial Safety and Health Act, and the Japanese industrial standards that also deal with how to produce, store, and the safety requirements related to hydrogen systems. These are just examples of international codes. Check your local country or jurisdiction for your latest safety codes in your area. So with applications that contain hydrogen, the codes and standards encourage us to create hazardous mitigation analysis to feed into our hazardous mitigation plans. So I created a few bullet points that outline some of the safety items that we need to consider for our hazardous mitigation analysis. The first one is monitoring hydrogen concentrations. And so we should know exactly what our concentrations are, if it has to do with normal operation or looking for leaks or monitoring safe levels within a specific space or room. And as we discussed, there are a variety of different sensors to help us do this. And of course, depending on your application, then you have to do a detailed analysis on which sensor actually meets your requirements. Second, we have to provide proper ventilation to hydrogen-containing areas. Adequate ventilation is essential for preventing accumulation of gas. Hydrogen gas is lighter than air, so it will rise to a ceiling if it's indoors. And as a result, ventilation systems should be designed to extract hydrogen gas from the upper part of the room. And of course, hydrogen monitoring and ventilation can work together, where the monitor can trigger the ventilation system to turn on when an unsafe level of hydrogen is detected. We also must use proper equipment and procedures. All equipment and procedures used for handling hydrogen should be designated to minimize risks. And this includes using properly designed and maintained equipment, as well as following the safe operating procedures. And then, of course, we have to provide training to our employees. And all employees who work with hydrogen should be trained on safe handling of the hydrogen gas. It should cover topics such as the properties of hydrogen, the hazards of hydrogen, and safe handling of the hydrogen equipment. It should also include on how safety equipment works. Based on your configuration of your safety equipment, your employees should know about how that safety equipment operates, and they should also be able to recognize when it is not operating properly. They should also know about enunciation from that equipment and how it will enunciate to an alarm center that will allow them to take proper action. So the list of applications is definitely growing based on new technologies, either using hydrogen as a fuel or creating a byproduct of hydrogen or hydrogen used in specific applications for creating other products. The application can present challenges based on the environment, concentrations and cross sensitivities to other gases, and also having to abide by standards and regulations based on industry standards or regulations from authorities having jurisdictions. Sites that contain hydrogen or use hydrogen may need to create a hazardous mitigation analysis, which leads to the hazardous mitigation plan that may be required by your authority having jurisdiction. Review your local regulations and codes in your area for the requirements. And sensing and hydrogen technology is evolving. Keep up on new technology that may affect longevity, maintenance requirements, and also ease of operation. Thank you very much for your time today with this presentation.